many of you are in one of my classes? Okay, it's awesome. You're all going to get extra credit. For those of you that are in my classes, please make sure that you look on Canvas for the instructions about what you're supposed to write for this. A couple paragraphs about how it changes your feelings about math.
Just math, not
I'm hoping that this will be a life-changing moment for all of you.
Cough, cough, cough. There were no feelings or anybody.
All right. Any good talk has a prologue, not really, but this one does. Okay. Okay, I want to test you guys. All of you that are in my classes, every one of you have taken a multivariable calculus class. Everybody else, how many of you have taken multivariable calculus before? Great. How many of you remember what you did in that class? 2 of you. Great. Okay. I want you guys to help me, because we're going to write down a bunch of theorems here, and I want you guys to help me remember what they are. So I want to look at the Fundamental Theorem of Calculus, F-top. What is that? Help me write it down. I'll say f prime of x. dx equals what?
F of b minus f of a.
Good. That was Calc 1, so that's good. There's also the Fundamental Theorem of line integrals.
Really?
Yeah. Fundamental Theorem of line integrals.
Is that the integral over c?
This is the integral over c of the
gradient of
f, good,
dr
dot dr, where, I have to tell you what c is. It's some parameterization like this, where t ranges from a to b. So then this will be equal to what?
f of r of b minus f of r of a.
Very good. Okay. What's next? What's another theorem?
Green's theorem.
Green's theorem. Hey! If you don't remember any of these, just go ahead and open up your book to section 16.10. They're all listed there. Okay. But anyway, we're going to look at something about them. Green's theorem. What does that look like?
The integral over c.
I'm going to do the two-dimensional part first.
Okay.
So the integral over some region D of what?
Partial q partial x minus partial q partial y dA.
dA equals
The integral over a curve c of p dx plus q dy.
okay. Good. And D is some region in R2, right?
That is bounded by c.
With boundary curve C. And what does C have? Some kind of orientation. It's oriented counterclockwise, which means it goes around counterclockwise. What happens if it goes clockwise? What happens to the theorem? Yeah, one of the sides has to get a negative. Okay. All right, great. So there's Green's theorem. We're running out of room here. What's next? Stokes theorem. Stokes is his last name, so the apostrophe goes on the outside. Where's Bob? He got on my case for this the other day. Okay. Stokes theorem.
Isn't it Stokes's?
Stokes' theorem.
Yes.
Mr. Montiel. Stokes' theorem. And, all right. And what does it look like? Yeah, it's the surface integral over S of what again? Curl of a vector field F dot D, and this is the arrow S, right? The vector version. And this equals the line integral over C of what? F dot dr. And C, S is some surface in R3 with boundary C. And what's true about their orientations? What's the orientation on the C? It's telling you which way to traverse it, right? So it's kind of picking a tangent vector direction. How do you orient a surface? I get
Is it
the normal. It's the normal, right? The normal tells me which way to orient the surface, right? There's only 2 choices at each point, one way or the other, right? The orientation on C and S will, what we'll say, coincide or complement each other or whatever, or be consistent with each other, if the orientation on C produces the orientation on S by a what? Do you remember from my class?
the right hand rule?
The right-hand rule, okay? If it follows the right-hand rule, we we say that that orientation is a positive configuration. So they're positively oriented if the orientation on the boundary curve induces the orientation on S. Does that make sense? So with boundary curve C positively oriented. If the orientations don't agree, what happens to the theorem? One side's got to get a negative. Okay, and the last one?
And I think there's one more thing to explain. DS is a normal.
Yeah, that's what this means. It's a normal
normal.
vector. Yeah, normal. Yeah. So the orientation on C, the tangent vector, rotation around it, has to produce the normal vector that's contained in the ds. So the dr has the tangent vector. So you can almost think of this as f dot the orientation on C, and this is the curl of f dot the orientation on the surface. Okay? And then there's the divergence theorem, right? And what does the divergence theorem say? Yeah, let's do the triple integral first. Over E of dv equals
The double integral over S.
Good. I am really happy how many of my Calc 3 students I'm hearing right now, because you guys must have done really good on the test this week. Either that, or you did terrible and you looked it up and now you know. I don't know which one it is. Okay. Here, E is some surface, or not surface, some space in R3 with boundary S, and S is oriented outward. And outward makes sense because S has to be a closed surface, kind of like C had to be a closed loop, right? So an outward orientation and inward makes sense. The outward is the one that points towards the unbounded region that it bounds. Okay? So, what do you notice about these things? Well, that's what the point of this talk's going to be, is we're going to identify that they're all actually the same and see why they're the same. I notice here, what do you notice about the left-hand side of each equation? How many integral signs are there compared to the right-hand sign? Yeah, there's always one more on the left than there is on the right, and that's why I wrote it that way. So it's like I have a higher dimensional integral over here. And then what about the integrands? How are they related? The integrand on the left compared to the integrand on the right. The one on the left is always some kind of derivative of the one on the right. Okay, so here you can see it's directly the derivative of the things I'm plugging in here. Here it's the gradient, because this is an f of like xy or f of xyz or something. And over here, those are derivatives of the components. Here you get a curl, that's a derivative operator, right? And over here, a divergence, that's also a derivative operator. Okay, so you see, basically what these theorems are all doing is that I can lose one dimension in integral if I go up one layer in derivatives. Does that make sense? You kind of think of it like that. Okay. So let's talk about these types of integrals for a minute and see what they actually are. I'm going to use this board over here so that the camera picks me up. I'm going to ask you some Calc 1, Calc 3 questions again. I'm not done with the quiz yet. Okay. What does this actually compute? What is this?
The area under the curve.
Right.
Between A and B.
So I've got some curve here, f of x. I've got some space here, A, some space here, B, and it computes this area here. Okay? So this is a 1D integral. I'm going to call it 1D for a good reason. What's one-dimensional about this? The domain here is one-dimensional. Okay, the thing that's over is 1D. 1D domain. Okay? A 1D integral computes what?
An integral?
An integral. It was there. I know it's not normal without the end, but okay, a 1D integral computes what? Area. Okay, it computes area. What's the dimension of area? It's 2D. So a 1D integral computes a two-dimensional thing. Okay? Okay, let's take a look at a double integral. What does that compute?
The volume under surface.
Yeah. So I've got some surface here that has some shadow. Here's the surface. This is some region D here. This surface here is z equals f of x, y, right? And it's computing this volume that's sitting above it, okay? Everything that's inside there. Something like that. Okay? That looks terrible. But it's the volume underneath that, okay? So what kind of domain does this have? 2D domain. And so I'm going to call it a 2D integral. It computes what kind of object?
3D volume.
Computes volume, which is 3D. Where's it going with this? Where do you guys think we're going to go?
A 3D integral?
3D integrals, cool. A 3D integral, I can't draw a picture for, but it's something like this. The domain is 3D. So what does this 3D integral compute?
Hypervolume?
Yeah, it computes a hypervolume. Which is what dimensional? 40. Now where do you think I'm going to go?
The n dimensional?
If you think I'm going to go up, you're wrong. I'm going to go down. Given the pattern that you see here, what would you expect a 0D integral to compute? A 1D length. Okay. A 0D integral should compute a length. So if I have 2 points here, A and B, that is a zero-dimensional domain because they're just points. There's no length here. If I integrate some function over this, and I'm just going to call it f. Notice I don't have a dx or a dv or anything because there's no other dimension to multiply by. The dimension of this integrand is always one-dimensional. This is one-dimensional. That's why I get a two-dimensional thing out. This is one-dimensional because it's a number. This is two-dimensional, and that's why I get a three-dimensional thing out because it's a dx, dy. See, that's two different dimensions, two lengths there. This integrand is one-dimensional, but dv is three-dimensional. Do you see that? That's why I get a four-dimensional thing out. And then it's just like an infinitesimal summation. Okay? So here I have my one-dimensional height, but there isn't anything to multiply by because these things are zero-dimensional objects. Does that make sense? So if I do a 0D integral over a zero-dimensional domain, what should I get out? The distance between those two things, which, I'll write like that. It's the difference between the values at each of those points. That's the difference, the distance between the number at B versus the number at A. Immediately, what do you notice about the right-hand side there? Have you seen it before?
Yeah, fundamental theorem.
Where?
Fundamental theorem.
Yeah, it's the other part of the fundamental theorem of calculus. Wait. That means that the fundamental theorem of calculus had a 1D integral on the left and what kind of integral on the right? A 0D integral. Okay? So it looked in that pattern just like Green's theorem or Stokes' theorem or the divergence theorem. It had a higher dimensional integral on the left and a lower dimensional integral on the right. Does that make sense? Okay? Cool. Now, we need a couple of other pieces here to start recognizing some more of these similarities. We need to know what a boundary is. And we've kind of used that word a little bit here, but let's identify a little bit more about what the boundaries do and maybe add some notation. Okay? We're going to talk about boundaries. This is the part of the talk you have to respect. Here till Thursday, folks. All right, so if I get a 1D interior, right, of this interval here, what do you notice is the boundary? What kind of object?
Points.
They're points, and points have how many dimensions? 0D boundary. Okay, in fact, if I squiggle the interior, I still have a 1D interior. Why is it one-dimensional on the interior? What makes it 1D? Kind of. How many points does it take to describe an n-dimensional object? How many numbers? It It takes n numbers to describe an n-dimensional object. In fact, that's what dimension means, is how many coordinates it requires to describe a point. It takes one number to describe a location for a curve like that. That's why you can parameterize it. Right? You parameterize the curve, you're assigning a number to each point, which is a coordinate system, and that's why it's one-dimensional, because it only took one parameter to do it. The surface takes how many parameters? Two, so it's two-dimensional, like the surface of the Earth. There's an easy way to parameterize the surface of the Earth. We use what? Latitude and longitude. Two numbers identifies the location on the surface of the Earth, so the surface of the Earth is two-dimensional. Does that make sense? Okay? So the dimension is how many numbers it takes to describe a location. Okay? So here, it kind of breaks down a little bit at 0 because it's just a point, right? There's nothing to describe anything. That's why it's 0 numbers. Anyway, again, 1D interior, what's the boundary look like?
Zero-dimensional points.
Zero-dimensional boundary. BDY for boundary. Okay. If you notice, the Fundamental Theorem of Calculus handled domains that looked like this, right? Straight line domains on the x-axis, that's all you could handle in Calc 1. So it was sort of like a flat 1D integral, flat 1D case. Line integrals allowed that line to go wherever you want it to in 3 space, technically n space. Doesn't matter what the dimension is of what it's embedded in, still a one-dimensional object, it's just wobbling around. So the Fundamental Theorem of line integrals is really the wobbly version of the Fundamental Theorem of Calculus. Does that make sense? Okay. In fact, you'll notice maybe there's something else about Green's theorem and Stokes' theorem too about that. Okay, we'll talk about it in just a second. First, I'm going to introduce some notation here. In this case, I'm going to call the interior, or the whole region itself with the boundary M. In this case, it'll be the interval A to B. I'm going to call the boundary partial M. And there's a reason why you use the partial, and you're going to see it by the end of the class today. Class, doc, whatever. Okay. This means the boundary of M. So what's the boundary of M? This is the boundary. What would be the boundary of those? The 2 points, A and B. Notice I use braces. That's just those 2 points. That's the boundary. If you want, M is actually the entire, over here, M is the entire parameterized curve, right? Where T ranges from A to B. So in that case, what would the boundary of M be? Is it A and B?
R.
It's R of A and R of B. This one's a lot more hip than that guy. Jen's dying. She's like, I wish I had come to this talk. Okay, that's pretty cool, right? So we got boundary stuff. Okay, let's talk about flat surfaces. Okay, so if I've got D here with some boundary C, notice what's the interior like? That's how many dimensional? 2D interior has what kind of boundary? 1D boundary. So the boundary goes down 1 dimension. Do you see that? So the boundary between these things. So I'm going to let M be that D region. Okay? So then the boundary of M would be C. Does that make sense? Okay, not too bad. Let's take a look. And Green's theorem works on these guys. This is the kind of domain you get in Green's theorem, and the boundary is the domain of the other side, right? So it relates a flat 2D integral to a curvy 1D integral. And let's take a look here. So what if I have a surface S? Okay? It still has a boundary, right, which I'll still call C. The interior is what dimensional? 3. Careful.
Interior?
The interior is this is like the surface of a balloon. It's still 2-dimensional. There's nothing inside. It's still just that surface. It only takes two numbers to identify a location, right? So this is still a 2D interior. It's just wobbly, okay? And it has a 1D boundary. You see that? So here in this case, M is S, and partial M would be C, okay? So I'm going to use this partial M notation for the boundary. There's one left. Oh, by the way, so Green's theorem is on top of this. It says the double integral on D is equal to the integral around of stuff, right? Stokes' theorem says the surface integral on the surface is equal to a line integral around. It turns out that Green's theorem is basically the flat 2D case. Stokes' theorem is the wobbly 2D case. These are all technical terms.
Mathematical lexicon, right?
This is how sophisticated we are here. All right, so what do you think would be next then?
The flat 3D case.
The flat 3D case, which is what Divergence Theorem works on. So this is, I've got a flat interior, which looks wonky because what does flat in 3D kind of even mean? Doesn't have to even be polyhedral, just pretty much what you can imagine is flat. Because to be wobbly, like think about it, to make one dimension wobbly, we had to go where? To 2D, to see it. To make 2D wobbly, we had to embed it into 3 dimensions. That's why you made the mistake, because we're putting it in 3 dimensions. So to make 3-dimension wobbly, we'd have to go 4D, and we can't draw it. And that's why we don't make you do it. That's why you only go to the 3D flat case, and we never teach you the 3D wobbly case, because you'd have to do a 4-dimensional integral, you'd never be able to see what it was. Not to mention, by that time, multivariable calculus is going to run a little long, and it's time to do that. Okay. The interior here is E, and it's 3-dimensional interior. It has a boundary that's what dimensional? 2D, and it's called S. So 2D boundary, it's called S. So in this case, M is what? E, and partial M is S. Okay, does everybody see the pattern so far? Okay, this is how we're going to build all this stuff up. There's one last piece we need to start with before we start seeing something interesting about the fundamental theorem of calculus. And I need you guys to remember back in Calc 1 when you did linearizations, okay? Local linearization or linear approximations, we introduced a really cool thing called the differential. You guys remember that? Okay? If, let's talk about differentials for a second. In Calc 1, it wasn't that bad. If f is a function of x, then df was something. What was it?
dx?
It's not dx. There is a dx in it, but it's missing something.
F prime of x.
F prime of x dx. Okay, remember? This is the, it essentially is a shorthand way of writing the local linearization. This is like y2 minus y1. This is the slope times x2 minus x1, so it's a line, right? This is an infinitesimal difference in the height and an infinitesimal difference in the length. Usually the way it's presented in Calc 1 is this is really the differences on the tangent line. And the reason why they can expand it that way is because the tangent object preserves the infinitesimal relationship. Okay? But really, we're going to think of those as being really, really tiny changes. Okay, so what we're saying is that if you have a function and you change the y value a little bit, then, sorry, if you change the x value a little bit, to find out how much the y value changed, you take that change in the x value and you multiply it by the slope, the derivative. That tells you how much the y value changed. Does that make sense? Okay, we're doing everything in the tiny. So we can use the chain rule to help us figure out what to do if we have multiple variables, and that's what we did when we did local linearization and multivariable calculus. So if I have f of x, y, what's df in that case? Looks very similar. So is it f prime of x? Partial f, partial x times dx plus
Partial f, partial y times dy.
dy. To kind of preserve the same notation, I'm going to rewrite this as df dx. And in fact, at that point, it's always why we use that notation. Did you see it? You cancel the dx. Wait, I was told that's not a fraction. It actually is. It's just a fraction of infinitesimals. So they behave a little different. Okay? But some things are the same. So what do you think here? In fact, you can almost think of this one as sort of being the partial part that you get, the partial of f that you get from x, and the partial of f you get from y. Hence the name partial derivatives. Okay? What do you get if it's f of x, y, z? What's df in that case?
Partial f, partial x, dx, plus partial f, partial y, dy, plus partial z, partial f, partial z, dt.
Good. And of course, you can see what to do if we go to higher dimensions, right? Okay, this is called the differential. In another land, we're going to call it the exterior derivative of talk about that in a minute. This is actually enough to identify and show you that the fundamental theorem of calculus and the fundamental theorem of line integrals are actually the same thing exactly. They don't just look similar, they are literally the same theorem. Okay? So let's see what happens. Fundamental theorem of calculus again. Well, this takes a function y equals f of x, that's your surface or curve that you're trying to integrate underneath. We can figure out df. What's that going to be?
F prime of x dx.
F prime of x dx. Let's look at the domain. The domain in this case we'll call M is going to be the interval a to b, right? So what's partial M going to be?
The set point A and B.
The set a and b. According to what we've written here then, the integral from a to b of f prime of x dx, okay, looks an awful lot like that. I'm actually going to give this a name. I'm going to call this guy, instead of calling it df, I'm going to call it omega. Okay? Sorry, I'm going to call it d omega. I'm going to let this guy, f of x, be omega. I'm going to call this then d omega. I'm going to use that, there's a good reason why I'm going to do that, is because I'm going to use this omega for a lot of different types of things, not just functions. Okay? So let's let omega be f of x, then d omega would be this, right? This is now the integral over that boundary, that domain, right? So I'm going to borrow the kind of notation we did for line integrals, and it's just the straight line, that's the x-axis, right? So I'm going to put an m down there instead of integral from a to b. So this is the integral over the line m, or the line segment m, of what? What's f prime of x dx?
D omega.
D omega. Okay? On the other hand, f of b minus f of a, what's that? That's another integral. It's a 0D integral over what? Over a to b, over a and b, right? Of
Omega.
of omega. I'm going to write f here just so we can see it. This right here is partial m, so this is the integral over partial m of omega. So if I use this substituted notation, right? This tells me that this looks like the integral of m d omega is equal to the integral over the boundary of m of omega.
Why not plus?
Huh?
Why not plus? F of b plus f of a.
Well, it's supposed to be a length. We talked about that already. You missed that part of the lecture, Bob. Sorry.
Oriented.
It's oriented length, yeah.
Is the length or the points?
The sort of difference, the difference between the values at the points is the length on that real line that they're mapping to. Anyway, it made sense when you weren't here, Bob.
Thanks a lot, you're okay.
All right, let's compare this to what happens with the fundamental theorem of line integrals, okay? In this case, what's my m for a line integral? It's going to be that curve C, right? And what did we say that looked like?
R of t.
R of t, right? And then partial m was R of b, right? Okay. It's kind of oriented because it's telling us which way from where we're starting to where we're ending. So the oriented length we want that's consistent with the orientation on C, right, is terminal minus initial. That's the oriented length that's consistent with it. Okay. Now we also need to take a look at some other components here. When we do this integral here, line integral, we're going to have something that looks like this, right? So we need to talk a little bit about what the dr thing is. What is dr? You may remember?
F prime of t.
Not f prime, it's r prime of t dt, right? But r is what? It's, let's do the 2D case to make it easier to see. It's x of t, y of t, right? Really, you could have z of t, w t, whatever you want, okay? So r prime of t then is just the derivative of each of those pieces, right?
X prime of t dt plus y prime of t dt.
Yeah, the dt will now then distribute in. I'll get x prime of t dt, y prime of t dt. See that? And what was x prime of t dt? What does that look like? If the function's x prime of t dt, functions x of t, x prime of t dt,
Looks like x prime of x dx.
looks like this. If it's x of t, x prime of t dt would be dx, right? So this right here is dx, and this one would be dy. So this is actually dx dy. Okay? You with me? Okay? What's the gradient of f in the 2D case? It's also another vector, right? Partial f, partial x,
and partial x.
partial f, partial y. So what would the gradient of f dot dr be? This is dr here. It would be partial f, partial x,
X prime
dx plus partial f, partial y, dy. And have we seen that before? What is it? It's df. So I'm going to let omega, again, be f of xy, or f of xyz, whatever you want. Then d omega is this guy. See that? That's what this is. So d omega is actually the gradient of f dot dr. See that? Okay? Which means that if I write all this in that same notation, the line integral over c of this becomes the integral over m of d omega equals the difference of these guys, which is the zero-dimensional integral over the boundary of f, which was the height here. Because remember, this is the thing that ends up on the right here. Boy, I'm running out of room. The thing that ends up on the right here is f of r of b minus f of r of a. So it's the difference on f at those values there.
Can I fix my confusion and say outward unit normal at those ends?
Yeah, there you go. So then what would be the interior here?
Omega.
It's omega because that's what the f is, right? And look at that now. Look at that compared to that. It's the same thing. That's pretty handy, right? Pretty cool. And it's not a notational trick, by the way. We defined the differential first, and then identified it here. You see that? This is not a notational trick. Okay? That actually is the object that's there, is the differential. Okay? All right, what we want to do now is we want to go and talk about Stokes theorem and divergence theorem, which means we've got to have higher dimensional stuff. So we've got to know what happens to a higher dimensional differential. Does that make sense? This is all sort of 1D still. You see that? It's got a dx and dy. So I got to introduce what's called a wedge product to you guys. Kinda, yeah. It actually behaves a lot like the cross product, though. So if you know a lot about the cross product, you'll be familiar with some of the properties here. So let's talk about the the wedge product for a minute. The wedge product. Okay? I'm going to do this in n-dimensional space. So say I've got coordinates x1 to xn. Okay? So it could be however many, 2, 3, 17, whatever you want. I'm going to tell you this is an object that's called the wedge product. I'm not going to go really carefully into what its definition is because it's not super important. I just want, for our discussion anyway, I just want to tell you about sort of what its properties are. Okay? This is called a wedge product, hence the wedge thing in between it. And what its important properties are is it basically behaves like a cross product, meaning that it's additive in each position, just like the cross product is. So I can separate sums out, right? A cross B plus C is A cross B plus A cross C, right? Same thing here. Scalar multiples pop out. And what happens in a cross product if I flip the order?
Negative.
I get a negative. This has that property as well. So it's additive and it preserves scalar multiplication. How many of you have taken linear algebra? Few of you? What type of functions, multiplication, I can't talk and write at the same time, multiplication. What kind of functions are additive and preserve scalar multiplication? scalar multiplication, what kind of maps on them preserve those operations? Linear maps. Okay, linear maps preserve them. So in other words, this is linear in each position, okay? And if I flip the order, so here's the same thing I wrote there. If I flip the order, I get the negative of whatever this object is, okay? Don't worry about what the actual object is, just it has these properties, okay? I can actually do this for higher dimensional wedges, and this is where it's a little bit different than a cross product, because a cross product I can only do two. Well, I can do it if I tell you how to associate it, but what I'm going to do here is, if I have something like this, okay, this has the property that if I rotate any pair, I get a negative, okay? So if I switch these guys, or switch these guys, or switch these guys, which is really switching those guys and switching those again, so I got to be a little careful. So it's really pairwise switches, okay, switches to a neighbor, will create a negative. So if I switch this guy and that guy, I'll get a negative here. And then if I switch him with his neighbor, what happens? I get another negative and I'm back to where I started. So, in other words, the order, they're kind of related on how they're ordered. All right, and I got to be careful with that. So what I'm going to do is I'm typically going to try to order them in sort of alphabetical order, or if I have indexes, numerical order. Okay, just to kind of give myself a standard way of ordering it. So I'll have to rotate sometimes in order to get it that way, which might introduce some negatives. You with me? Okay. We're going to call these n forms. Okay? A zero form is just a function, like f of x or f of xy. There's something that doesn't have any differential pieces on it. A one form is something that has one dimension worth of these dx things. Anybody ever seen anything that looked like that before? Yeah, that's a one form. Okay? What do you think a two form is going to be then?
P dx dy?
Yeah, p dx dy. I'll have dx wedge dy plus q dx wedge dz, maybe? And r, what?
Dx wedge dz? Or
Or
dy wedge dz?
dy wedge dz. Those are the only ones I get, because the fact that it rotates, can I ever have a dx wedge dx? What would that mean? If I switch those, I'd get the guys equal to his negative. What's the only thing that's equal to his negative?
Zero.
0. So if I ever have a repeated index, if I ever have a repeated guy, it's toast. Okay? So if I'm in 3 dimensions right here, I can do 3 forms. What would a 3 form look like?
That P dx wedge dy wedge dz?
Good. Could I do a 4 form in 3-dimension coordinates?
No.
No, why?
You have to repeat them.
I'd have to repeat something. So it'd be 0. Any 4 form, 5 form, any higher dimensional form with higher than the dimension of your space is always going to be 0. Okay? So I can always, so if I'm in an n-dimensional space, I can go from 0 forms to n forms, and that's it. Does that make sense? Okay? All right. Now that I've got this, we can take a look at something called the exterior derivative. The exterior derivative takes a n form to or a k form to a k plus 1 form. It does it in a very particular way using differentials. Okay? If I start with omega being f, so I've got a 0 form here, I can send it to a 1 form by applying the differential property, right? That would be d omega, which is df, which we know is f prime of x dx, or whatever you have, if it's 1-dimensional. 2-dimensional would be partial f partial x dx plus partial f partial y dy. So basically, if you want, you can think of it like this. If f is a function of n variables, d omega would be the sum from j equals 1 to n of what? Partial f, partial x j times dx j. See that? That's what the exterior derivative would be in every case. The exterior derivative from a 1 form to a 2 form is also not too hard. What it does is the following. From a 1 form to a form. So that means I start with omega looks something like p dx plus q dy, something like that, okay? What it's going to do, so if you want, maybe I could even write this as a sum, instead of calling it p and q, let's do an n-dimensional one, where I've got p1 dx1 plus pn dxn. Boy, I'm really having a hard time not putting the indices on a superscript. In differential geometry, sometimes they put them up there. Anyway, there's a reason, but it's not relevant. Okay, anyway, so p1 dxn all the way to pn dxn. Okay, this is what I get here. I could then write this as the sum of I equals 1 to n of pi dxi, correct? I'm going to define d omega to be the sum from I equals 1 to n of dpi wedge dxi. So I exterior differentiate the coefficients. Okay? But the exterior derivative is something like that. So this really ends up being the sum from I equals 1 to n of the sum from j equals 1 to n of partial pi partial xj dxj wedge dxi. You see that? Okay? And since it's linear in that slot, I can pop them all out and move the sums around so I get just these pieces out. Does that make sense? In fact, those of you that are familiar with linear algebra know that vector spaces are things that have a basis, and you can write them as linear combinations of those. This is a vector space whose basis vectors look like these. Okay? All right? Let's give this a try. Do something concrete with it, because I think I might have just lost some of you. Okay? Let's go back and do that pdx plus qdy thing. Okay, boy, I'm going to have to do a part 2 of this. This is going to run over. df then would be, well, I got to do dp on dx. So it ends up being dp wedge dx plus dq wedge dy. But dp is what? Partial p partial x dx plus partial p partial y dy wedge dx plus, and what's dq? Great place to get ice cream. But partial q partial x dx plus partial q partial y dy. I'm very proud of you, Jacob, for coming to that joke before I got there. Wedge dy. Okay? All right, so we got that. Now, it's linear in this slot, so I can break it across the sums and pull the things out. So here, when I do this guy, he'll get hit with the dx, but then I got a dx wedge dx, and what happens? Zero. So that part is toast. Same thing here with the dy component. Toast. So the only thing I get left is what?
Partial p partial y dy wedge dx plus partial q partial x dx wedge dy.
And what did I say about how I wanted to order these? I always want to have them in alphabetical order. So I'm going to switch this guy to dx wedge dy, and that puts what?
Negative.
A negative. So I get negative partial p partial y dx wedge dy plus partial q partial x dx wedge dy. Now they have the same thing, so I can factor it out, and I suddenly get partial q partial x minus partial p partial y dx wedge dy. Does that look familiar to anyone? Oh my gosh! That looks like Green's theorem. Okay? All right. What do you think happens if I do a three-dimensional one and get p dx plus q dy plus r dz? Say it louder. I almost get a curl. One of the signs is off. But it's actually supposed to be off. Because in Stokes' theorem, what's in the integram? It's the curl of f dot the normal vector. The normal vector also has a sign problem in the same slot. So when I dot them, the sign problem goes away, and I suddenly get the integram in Stokes' theorem. So it's not that df of p dx plus q dy plus r dz turns out to be the curl of f. What it ends up being is the d omega of that becomes the integrand of Stokes' theorem. Okay? So let's maybe move to that, because I'm kind of running out of time here. What do you think I do to go from a 2 form to a 3 form? The 2 form will just have it'll be like a sum like this. I'll P1, we'll say, let's do it this way, just so we can see it real quick, and then I can do those last 2 computations so you can see the last few bits here. If I have P1, and instead of putting dx1 here, I'm going to order it by the guy it's missing, okay? So I'm going to write dx2 wedge dx3, or dy wedge dz kind of thing, okay? Or if I wanted to do it in high dimensions, I do P1, this would be dx2 wedge dx3, and then I do dx2 wedge dx4, and so on, okay? But in 3D, it's kind of easy to see. I'm going to do this. I'm going to go P dx2 wedge, dy wedge dz plus q, who should be missing here?
Y.
The y, so I'll have dx
dx wedge dz
dz plus,
r dx wedge dy.
yeah, okay? That's what I'm going to have sort of instead. And then nice things will happen with this. And so when I do the exterior derivative on this guy, basically what it is, I do the exterior derivative on P and wedge it with that. Exterior derivative on Q, wedge it with that. Exterior derivative on R, and wedge it with that. And since this already has a y or a z, the only thing that survives from this will be the x part, right? The only thing that will survive from this will be the y part. The only thing that survives from this is the z part. It does get a sign mess up in the middle because of we got to shuffle these around so they're in alphabetical order. But that's pretty close to the divergence, isn't it? Okay? Partial f, the first guy, partial p, partial x, plus partial q, partial y, plus partial r, partial z. It's pretty close. It messes up in the middle, but we'll be able to correct for that. Okay, so that's how the exterior derivative keeps working. We just exterior differentiate the coefficients, wedge on it, and then break it up and expand in sum. Okay? So let's investigate a little bit. That's actually about time. Are you guys interested? Should we keep going? Or do you guys want to? Okay, all right. We'll keep going since it seems like everybody's still kind of interested. All right, let's take a look at Green's theorem. Okay, so Green's theorem. We've got omega is going to be p dx plus q dy. Okay, which is one of those integrams that we saw. So what would d omega be? We just did that. D omega would be partial q partial x minus partial p partial y.
dA.
It'll be dx wedge dy. Now, you're going to have to trust me on this part, but this I'm going to identify that with dA. It actually turns out that actually is what dA means. We just didn't tell you there was a wedge product in it. Okay? But anyway, that's actually going to be what the dA is. So we'll identify that with that. So this will be this guy times dA. And so in that case, C is, what's M going to be for Green's theorem? You guys remember this is the flat 2D case, so I got a D and a C. It's going to be D. Partial M is going to be C. When I do this partial, I got to be a little careful because there's some orientations that are floating around here too. The partial refers to the positive orientation of it. So if you pick an orientation on D, which in this case is actually, what's the normal vector on this guy sitting on R2? Straight line up. It's the Z guy. It's K. So if I pick that as the orientation on the D part, the orientation on the outside is the one that coincides with it, and that's actually what we mean by partial M. It's not the boundary on its own. It's not just a collection of points. It's the inherited orientation as well. Okay, so partial M is going to be C oriented counterclockwise. Does that make sense? So you end up with this, and then Green's theorem, which is this double integral over D, we'll talk about this in a minute, partial Q, partial X, partial P, partial Y, dA, is really going to be the double integral over what? M, because D is M, of what's this term? D omega. Now, this is going to generalize to however many dimensions you want. How boring do you think it's going to be if I have to write n integral signs if I want to do an n-dimensional integral? If you do a million-dimensional integral, you're going to write the integral sign a million times. Kind of boring and not really helpful. So instead, for higher dimensions, we're just going to still only use one integral sign, and we'll just let the dimension of the thing we're integrating over tell me how many integrals are really there. So I'm going to rewrite this with just one integral sign. That's the integral over m d omega. The line integral of p dx plus q dy, well, that's literally the integral over what? What's c?
Partial m
Partial m
of omega.
of omega. And so this theorem again becomes the integral over m of d omega equals the integral over partial m of omega. That's exactly what the fundamental theorem of calculus was, and the line integrals. Think it's going to keep happening? Let's do Stokes. Let's find out what happens here. I'm going to give you guys a result here to help you out. If f is equal to p dx plus q dy, let's call this omega, not f, plus r dz, then, let's see, is that actually what I want to call omega? Yeah, I'll call that omega. Then d omega will turn out to be partial r, partial y, minus partial q, partial z, dy wedge dz, plus partial r, partial x, minus partial p, partial z, dx wedge dz, plus partial q, partial x, minus partial p, partial y, dx wedge dy. And you can figure that out just by using the formula we did before. Now this is almost the curl. The coefficients here are almost the curl. The middle guy is backwards. See that? If you remember what the curl looks like, I'm sure you all do, right? Okay. The middle guy's backwards. So let's take a look at what happens though. Because when we move into Stokes' theorem, we suddenly get something other than dA. What do we actually get?
dB. Or
We get ds, right? Stokes' theorem is the surface integral of the curl of f dot ds equals the line integral of f dot dr. Okay, I already know f dot dr kind of works out nice, but let's take a look at what ds would be. Now ds, if I have a parameterization r of uv, ds is ru cross rv dA. But what was dA in the uv coordinates?
dx wedge dy.
Well, in this case, it'll be du wedge dv. Okay? For the same reason we had dA was dx wedge dy a minute ago. But r of u, of course, is just equal to x of uv, y of uv, and z of uv. Right? Okay? So then if I compute ru, what will I end up with? Actually, no, but before we do that, let's take a look here. What's dx in this case?
R prime.
Partial x, partial u,
du.
du, plus
Partial x, partial u dv.
partial x, partial v, dv, right? And dy and dz are similar. So let's see what happens if I do dy wedge dz. What do I get? It's kind of long and complicated, but I basically put this in this spot, put the z1 in for that spot there, and FOIL. Okay? The du wedge du terms cancel, the dv wedge dv terms cancel, and you end up with this quantity here. Partial y, partial u, partial z, partial v, minus partial y, partial v, partial z, partial u, du wedge dv. And you get something similar for dx wedge dz and dx wedge dy. Kind of running out of marker on this one. How are you going to need that? Okay. These guys right here become partial x, partial u, partial y, partial v, or sorry, partial z, partial v. If you guys need to leave, go for it. But if you're interested, feel free to stay. I'm almost done. Same thing down here, right? Partial x, partial u, partial y, partial, boy, half of it is just writing it down, isn't it? Partial x, partial v, partial y, partial u, du wedge dv. Okay, does everybody see that? Okay. If you were to compute ru cross rv and actually write it out, now we know that's a determinant of a matrix, right? ijk, partial x, partial y, partial z, and then you put the pieces down there. The sorry, I take it back, so this is cross product, so it's just IJK, RU, and RV. If you compute that out and then match it up with what you see here, okay? So this RU cross RV times DU wedge DV, if you compute that cross product and line it up with what you see here, this term turns into this. And you can see right there that it also has a negative in the middle position, which is going to end up canceling with the negative in the middle position here. Okay? So it turns out that the curl of F, which has these exact same coefficients but with a negative in that position, dot this vector will take the x coefficient in curl of F, which looks like that, hit it with this, then it'll take the negative of this guy, which is the y's curl position, right? Y value in the curl, dot this one, the negatives will cancel. Or rather, you get the curl version, hit it with this negative here, and end up with that. When you do the z part, you'll get this guy here, dot that, and you end up with this quantity right here. The curl of F dot RU cross RV du wedge dv is equal to this term right here, which is d omega. Okay? This right here is the ds. And so basically the integrand in the Stokes theorem turns into that. So here in the Stokes theorem, this right here becomes d omega. What do you think this becomes?
Yes.
We've already seen this already.
Or d omega.
If this is omega here, that is exactly what f dot dr looks like. Okay? This is omega. What's the s become?
M.
That's m. And this is partial m. And we already said they had to have consistent orientation. And so Stokes theorem ends up the integral over m of d omega equals the integral over partial m of omega. And I'll leave it as an exercise since I'm way over time. That if you do the divergence theorem, the exact same thing happens. Only it's in that case, you want to let omega be, well, let me write it down. In that case, you want omega to be this. So I'll give you the hint to start with the divergence theorem. Let omega be p dy wedge dz minus q let's see here.
dx wedge dv.
dx wedge dz plus r dy, sorry, x wedge dy. Do that with that negative in that position there. In that case, when you do d omega, you'll get basically the divergence of f, which is p I plus q j plus r k. If f is this, what you get here when you do d omega is the divergence of f times dx wedge dy wedge dz, which you identify with dv just like we did with dA. And then the divergence theorem is the triple integral over e, which e is m, of d omega, because that's divergence of f times dv, equals the surface integral, which is the surface is the boundary of m, of
Omega.
this guy right here. For the same reason this stuff worked, when you do f dot ds, you get the negative piece in the middle. And so this actually does become f dot ds, looks like that. Okay? And so you end up with the exact same thing. So I guess I lied. I did it for you, I suppose. Okay. So the generalized Stokes theorem is one line, basically. It says, and this is the end of the talk, I promise. The generalized Stokes theorem says that if omega is a k minus 1 form on m, and partial m is the boundary of m positively oriented, meaning the orientations are consistent, then the integral over m of d omega is equal to the integral over partial m of omega. And that right there contains every theorem you ever saw in calculus, every integration theorem you ever saw in calculus, in one tiny little line. Pretty cool, right? Thanks, guys, for listening to me.
Hey guys, thanks for watching my video today on Philomath Party. If you enjoyed today's video, consider giving it a like, and consider maybe subscribing and hitting that notification bell for this channel. It'll help us know what kinds of videos you guys like so we make more of them. Anyway, I hope you enjoyed today's video, and we'll see you next time.